Um, Welcome. This is Arvinth, and today I'll discuss the cutting-edge topic in cloud security. It's enhancing cloud security through continuous verification, a zero-trust approach to identity and access management. This presentation outlines the shift to zero-trust architecture and its integration with machine learning for a modern cybersecurity challenges. The traditional parameter-based security model is inadequate for today's hybrid work and cloud environment. Zero trust architecture based on the principle of never trust and always verify emphasizes continuous authentication and strict access control. This research explores the incorporation of machine learning into zero trust architecture to enable real-time threat detection, adaptive privilege management, and a robust behavioral analysis. The aim is to provide a secure, resilient, and compliant model suitable for evolving threats in cloud ecosystems. As the cyber threat evolved, traditional security methods have failed to keep up. Zero Trust architecture redefines the security by treating every access attempt as untrusted. Its key features include multi-factor authentication, micro-segmentation, and real-time threat monitoring. By continuously verifying each user and device, Zero Trust architecture minimizes unauthorized access and lateral movements in case of any breach, offering a proactive solution for a distributed cloud environment. The motivation for this research from two primary challenges. Addressing contemporary cybersecurity threats such as insider attacks and advanced persistent threats, ensuring robust security without compromising user experience by leveraging ML. ZTA can dynamically manage privileges, detect anomalies, striking the perfect balance between security and operational efficiencies. Our objective is to design and implement a zero trust security model integrated with machine learning techniques. The focus is on enhancing continuous verification, dynamic privilege management, and real time threat mitigation to secure modern cloud environments effectively. The aim is to confront contemporary cybersecurity issues. Considering contemporary trends in cyber threats, companies cannot stay afloat if they do not address both traditional and new threats that may rise. Improving operational efficiency by digging down its core machine learning integrated zero trust architecture guarantees efficacious risk adjusted access, allowing strict security to cohabit with organizational efficiencies. Uh, this study addresses a few critical questions. How can ML improve continuous authentication in a zero trust architecture? What is the role of ML in bringing operational dynamic privilege management and risk access control into an organization? And how can ML enhance threat detection in micro-segmented networks to prevent lateral movements and insider threats? In what way can continuous monitoring and behavioral analysis be integrated in a zero trust architecture, enhance real-time threat detection using machine learning? Existing studies highlight the importance of zero trust architecture for minimizing attack surfaces. Innovations like Zero Trust Federation enable context sharing for better access control. However, challenges remain in scalability, integration, and real-time risk assessment. This research extends the literature by focusing on ML's potential to address these gaps. Key gaps identified in this literature include high positive rates in endpoint detection and response EDR systems, and limited methods for sharing context in Zero Trust Federation, challenges in optimizing protocols for IoT and cloud systems. Our research addresses these gaps, paving the way for scalability, privacy, com- compliant Zero Trust architecture framework. We use two benchmark datasets, the CIC IDS 2017, simulating real-time world network traffic, including various cyber attacks like DDoS and brute force, UNSW NB15, containing detailed feature for intrusion detection such as flow-based and time-based attributes. These datasets enable robust ML model training and evaluation, ensuring real-world applicability. The datasets have been retrieved from the Kaggle. They are both of them are public datasets. So these datasets are used in this approach. Implementation. Our implementation follows a structured approach, pre-processing data to handle missing values and normalize features. We trained 6 ML models including random forest, XGBoost, and K nearest network neighbors, evaluating models using matrices like accuracy, precision, recall, and F1 score. The focus is on achieving high performance while ensuring scalability and efficiency. So the data sets that been used are have used the Google Colab for training the data set, filtering out, balancing, and then providing the end result, which is the accuracy. So here I have data loaded the data set from the Kaggle website, which is the network intrusion data set. Then I processed it, filtered it. This is a distribution graph of this data set. And I use the sklearn pre-processing label encoder to filter out all the features of the vulnerabilities. These are all the features that have been identified in the dataset. So I did a filter out and chose the top 10 features which has been identified to have the most network traffic vulnerability that flows in the network traffic in a data transfer within a cloud environment or within any local systems. So filtering out the features here, these are the features, validating the feature selection, and from here I have chose the um, data set and trying to predict the accuracy of each data set. This is a random forest data set. This provided with the accuracy of 0.999, which this is the dataset that I have used in my project. Meanwhile, I had to compare with other datasets to see which one has the most accuracy. This is a confusion matrix. This is a model training. This is 994 for the decision tree classifier, confusion matrix KNN classifier, and its accuracy of 0.997, logistic regression 0.992, XGBoost, and the rest data sets in this collab. Labeling the distribution graph and decision tree classifier accuracy and random forest classifier's accuracy, XGB boost accuracy, logistic regression and accuracy, Keen and classification accuracy, naive Bayes accuracy, random forest test DF datasets accuracy. So with comparing all the datasets and providing modeling them with accuracy, the implementation follows with load the dataset into the database, feature selection, handling correlated features, handling infinite and missing values, feature scaling and standardization, data splitting, machine learning, and modeling the training, and model evaluation. These step-by-step process has been took place in the Google Colab and finalized with accuracy, and I compared the result. So this is the result and analysis. The random forest model emerged as the best performer with accuracy, precision, and F1 scores nearing a 0.999. It ensembles nature ensures robust detection anomalies and reduces overfitting. XG Boost is another strong contender, offering faster training and excellent scalability for real-time applications. So I had went with a random forest classifier in my Streamlit application, um, which is this real-time application. This Streamlit application demonstrates the practical deployment of these ML models for a real-time intrusion detection. It dynamically analyzes network data, identifying threats, and enable rapid responses. This bridges the gap between the theoretical research and the actionable cybersecurity solutions. In conclusion, zero trust architecture combines with machine learning represents the future of cloud security while challenging like scalability and privacy persist. This research lays the groundwork for a resilient, adaptive, and the compliant security framework. The integration of ML ensures that organizations stay one step ahead of evolving cyber threats. As for the demo, the zero trust architecture finalized model is what I trained with the most accuracy provided from the random forest model with a 0.999 with a accuracy precision F1 scores nearing 0.999. And this is the Python file, which is a cloud prediction file. Here in this program, the finalized model has been used by the pickle load. So we are using this finalized model, which we had determined from comparing all the data sets, the random forest as its result as the best performer. We are using that model here for our Streamlit application to determine any anomalies in the network flow. So we run the file using the command python -m streamlit run dot cloud, and it runs on our local host. That's my local host with my port number. That's my IP address and local IP address and my local IP port. And these are the top 10 features that I have filtered out in the dataset. These top 10 features are determined by the vulnerabilities in all the datasets. So they happen to be the most attacked packet flows. In this, since it's my local system and it's not a cloud platform that has a lot of network traffic happening, uh, we're gonna I'm gonna give a demo of the test of how it works if there is a safe network flow and if there is any malicious network flow. So I'm choosing to put a packet that uh, does not have any malicious vulnerability in the network flow. So as we predict, it provides with a binning, which means clear, and which means there is no malicious activity in this network flow. So To determine any malicious activity in the network flow, there is one predefined network flow that has a vulnerability, which is this filtering values, featuring values. That provides with the result of malicious, which means there is a type of attack in this network flow, which might be a DDoS, which might be a injection, SQL injection. Any attack that's within the dataset in this network flow will be determined as malicious. So this Streamlight application is integrated, should be integrated in a cloud platform of a big management company and had it run real time. So every network flow it's gonna give a real time result of either malicious or it's benign, uh, which gives concludes my project here with a real time threat detection in a cloud platform using the approach of never trust, always verify. Yeah, I conclude here with a thank you.